All right, welcome everybody. Now it's time today to finally start our study of the Fourier transform. And the reason why we're doing this is we want to understand linear filters. And what that is will become clearer later on. For now, we focus on the Fourier transform. And all that we have been doing so far can be seen as a preparation for things that are to come. However, last time I already said that we will, for a brief time, change our direction of attack. Up until now, we talked a lot about vector spaces and linear transformations in particular. And for today and the next session, we shall focus on calculus. Now, what is the Fourier transform? The way I am going to expose you to that is that we will first have a look at why it was developed. So, historically, this idea of the Fourier transform came about because people were looking for a tool, a way to simplify the treatment of certain differential equations. So historically it was developed as a tool for solving, let's say, certain differential equations. And I thought it is a good idea to acquaint ourselves with the Fourier transform following this historical development. And to make that clear, we will have a look at one of the marvels of mathematics. And by that, I mean that we shall consider this. Consider this. How did you, each and every one, learn about mathematics throughout your life? All right, let's look at that. How did we, everyone, learn math? Well, I would assume that in elementary school, after doing some elementary set theory, you may have learned about the addition and subtraction of numbers, right? Most likely. And then, once you mastered these concepts, you may have learned about the multiplication and division of numbers. Okay? And I would assume, I don't really know, but I would assume that that kept you busy throughout elementary school, and then when you entered high school, you learned about the idea of functions and the algebraic problems of solving equations. And you learned that you can extend these operations or this idea of adding two numbers or subtracting two numbers to the problem of adding functions and subtracting functions and multiplying functions and also dividing functions. So all of this applies to numbers and functions. Once you mastered that, I would assume that then later on you learned about differentiation, how to derive functions, and integration. Right? And one of the marvels of mathematics is that, well, we can understand this as ever more complicated things we learn about. One of the marvels of mathematics is that quite often we are able to reduce complex things, complex operations, two more simpler ones. So let me say a miracle of math is that we may, I call it, reduce complex or difficult, I should say, operations to simpler ones. And hopefully there is an instance of that you are all familiar with, and I will start by discussing that instance. Here is an example, and once you have seen that example, you immediately realize what I have been claiming here. Example, and the example is the logarithm, and well, I hope you are familiar with the fact that the relation, or fact, let's call it the relation, say ln of a times b. What am I doing here? A times b is equal to taking the logarithm of a and adding the logarithm of b. So the logarithm of a product is the sum of two logarithms. Now this allows for reducing, here is that word again, multiplication to addition. And that is to say that we have the following commutative diagram. If we are given, I make it with functions, two functions, say f of x and g of x, and we want to multiply them. So multiplication to obtain f of x times g of x. Instead of computing the multiplication directly, we may first take the logarithm to get ln f of x and ln g of ln g of x. I probably should stick to all these parentheses. Once we have done that, we may add these two new functions. Adding two functions is simpler than multiplying them. And we get ln f of x plus g of x, ln f of x plus ln g of x. Once we are there, we may take the inverse operation to obtain the product of the two functions. Right? So what have we just reminded ourselves of? That the arguably more difficult operation of multiplication can be reduced to the arguably more simple operation of addition if we apply a certain transformation to whatever we want to multiply. And in the case of multiplication, this transformation is simply taking the logarithm. Right? And once again, instead of doing this directly, we may take the following detour. Now, oh, and by the way, you know, it's not immediately true if these were functions that would involve negative values. So I may skip over certain details, for instance, the fact that these should be functions with values in R plus, but I hope that is okay, right? I don't have to mention this all the time. In particular, all of what we are going to do right now is well, how to say it, lacking mathematical rigor. This is not a math course. If it was, I would have to be much more careful about what I'm telling you here. What I'm trying to do in this lecture and the next couple of lectures to come is to really provide you with an intuition of what all of this is, and the really rigorous details are not our main focus of study here. I hope you can accept that. Now, we just saw an example of how to reduce multiplication to addition, doing something complicated in terms of something more simple. And here is another example, namely the object of our study, the Fourier transform. I'll write it like this from now on because it will occur quite frequently. What I am claiming is that there are more abstract transformations than the one we just saw, more abstract transformations that allow for reducing the operation of differentiation to multiplication. So this is my claim, and in order to be able to see that, we have to introduce one concept, again without mathematical rigor, but we need this because it is the kind of object we are going to talk about. The concept we need to accept or acquaint ourselves with is that a function, let's say it's a function that goes from the real numbers to the complex numbers. The complex numbers include the real numbers? Let's be general here. Such a function from R to C is called square integrable if we have that the integral from minus infinity to infinity of the norm of f of x squared dx is finite. That is to say that this integral is not supposed to evaluate to infinity. We are considering the integral of the function squared, and since we're talking about in general complex numbers, I'm taking the norm here. So if we square the norm and integrate over that, then the result should be a number and not the symbol called infinity. All right. If a function has this property, we say that this function is an element in a set that is called L2. And by now we should be familiar with the idea that we can introduce mathematically abstract concepts, and that these concepts define sets. We have talked about vector spaces and groups, which are very abstract kinds of sets. Now we are talking about all the functions that are square integrable, and we call the set of all square integrable functions M2. Now, once we have that, I can now claim, and I just claim it for the time being and not really prove it to you. That's again because this is not a math class, but we are interested in applications of mathematics, so we can gloss over certain things. But I can claim that every function that is square integrable. See the beauty of this? Once I have defined this set, I don't have to write down square, just write f is an element of L2, can be expressed as, now comes something outrageous. I claim we can write f of x as 1 over the square root of 2 pi times the integral from minus infinity to infinity over a function f of omega e raised to the I omega x d omega. First of all, we have met yet another Greek letter. This one here is the Greek letter omega, lowercase Greek letter omega. So the uppercase omega is this thing, and the lowercase omega is this thing. Note that this is very curly here, so this is not a W. Right? This curly thing is called omega. We have met this new letter omega, and then there is this thing here. What is that? I claim every function can be expressed like that, but in order to make sense of this, we should look into this. So let's look into that, where this function capital F of omega is given by 1 over the square root of 2 pi times the integral from minus infinity to infinity, and now we have f of x times e to the minus I omega x, and we integrate over x. So this thing here for the rest of our lecture today is called equation 1. And it is called, this function capital F of omega is called the Fourier transform of f of x. So once again, my claim is that if we're given any square integrable function, instead of talking about the function in the terms that we are given, say this could be sine x or whatever, instead of just calling it sine x, we could as well express it like this, which involves a function like this, which is defined as so, and this defines the Fourier transform of this function. And all of this will become clearer throughout the next couple of sessions. But for now, let us just accept that this is so. And now, let us briefly, I'll say something else, and then we will look at how or why this indeed allows us to simplify the operation of differentiation. Now, this thing is called the Fourier transform of x, f of x, and if you look at it, it is basically some factor times an integral. Integration is a linear operation, and we may express all of this in an operator notation, which is what I'm introducing right now. So in operator notation, notation, we write f of omega results from applying an operator, say calligraphic f. This is a very slanted f, and we apply that to this function f of x. This is, we talked about operators when we talked about gradients, right? There we had this nabla symbol, and we put it in front of a function, and that gave us something else. And here we have the same. We have a function, we put something in front of it. This is, you know, just a symbol. It's an operator. This is an abbreviation for this. Right? And now if there is a way of going from here to there, then ideally there would be a way of going from here to there. And so we just invert that operator, which is to say, we also may say that f of x is f inverse applied to f of omega. Okay. And this is just notation, but this is something I will use more or less frequently to not always having to write down this integral. Okay, I just threw in front of you the definition of the Fourier transform of a square integrable function f of x. We may, of course, try to Fourier transform the derivative of f of x. Let's see. So we can also, if this is fairly straightforward, we can also compute the Fourier transform of the derivative of f of x. And just to I don't know, simplify notation or reduce clutter, I will use f prime of x to indicate the first derivative of x. Right? Now let's look at what's happening here. We have, well, so we apply the Fourier transform to f prime of x, and then we just plug in everything we now have into the definition we met earlier on. So 1 over square root of 2 pi times the integral from minus infinity to infinity. Obvious only difference is that we have f prime now. E to the minus, wait a minute. Oh yeah, that's correct. Minus I omega x dx. I'm mistrusting my own notes here. So one more caveat. So far everything was correct, right? Now if throughout what is to come I might confuse these things, then it's your job to say, hey, wait a minute, okay? May happen, I hope it does not, but it's okay. So we're good. This is called equation 2 now. Look at it, I mean, all we did is we defined the idea of the Fourier transform. Right? We said the Fourier transform of a function f of x is given by some integral. Now we're interested in the Fourier transform of f prime of x. And the only thing we have to do, like really just syntactically, is to plug in f prime at the place where there was the f previously. Okay? So this is the Fourier transform of the derivative of f of x. Now we will evaluate this integral. We'll actually do some computations today. And in order to do so, we recall the rules of integration by parts. So let's do that. Recall the rules of integration by parts if you not really recall that, you may as well look it up at Wikipedia. So with everything that has to do with mathematics is quite reliable on Wikipedia. I can actually recommend it. This is to say, and hopefully you have seen this before, that we can, if we are dealing with the problem of having to compute an integral ranging from a to some v, precise here, v du. This is a very abstract way of writing down these rules of integrations by part, that this actually can be computed as u times v evaluated at the boundaries a and b minus the integral ranging from a to b u dv. Okay, so this is a very abstract rule in calculus. With respect to our problem, we will now, that is with respect to equation 2, we substitute, basically we say that du, we just do that, it's just a definition, is supposed to be equal to f prime of x dx, and we say that v is supposed to be equal or given by e to the minus I omega x. Right? These are two things that occurred in equation 2, and if we want to attack equation 2 using this general rule of integration, we can make this substitution here, right? And then we take it further and get. So if we do this, we find that u is f of x. Can you see that? Right. Because here we have du dx. So I'll do it once, right? Because this is not a course on calculus, but let me do it ever so quickly, just once. We said du is f prime of x dx, which is, and mathematicians will now, get a heart attack, but let's do it anyway, is the same as du dx is f prime of x, right? Can accept that. But this is to say that u is f of x, right? And if you're a mathematician, please excuse this. To us, we're doing applied mathematics, this is good enough. Okay, and it's true. I mean, like, even though this is fishy, it's okay. This really holds. And if we sort of compute the differential of that, we get that dv is minus I omega e to the minus I omega x dx. All right. This is basically what I just did now with the v. So if we use that and compare to equation 2, we get the following. Then, with this substitution, then 2 becomes, so we are interested in the Fourier transformation of f prime of x, and with what we just did, we find that we can express it as f of x e to the minus I omega x evaluated minus infinity and infinity minus 1 over square root of 2 pi times the integral f of x times minus I omega e to the minus I omega x dx. This is called 3. This is just, I just actually applied this rule of integration by parts using the substitution we just introduced to the equation we had in equation 2. We get this. And now recall that we are, for the purposes in this lecture series, interested in functions that are square integrable, since f of x is a square integrable function. We may assume, and I am very careful with my wording here, again, this is something we may assume because we are not mathematicians. If we were, then we have to be much more careful than we are right now. But we may assume that this function f of x goes to 0 as the argument x goes to either plus or minus infinity. This is a very, it's not actually a necessary property, but you know, let us assume that square integrable functions would have this property. If you think of it, it makes sense, because if a function grows for all eternity once the argument x approaches infinity, then the integral will not be finite. Right? So one way for us to think about square integrable functions is actually that they approach 0 if x approaches plus or minus infinity. Now, but therefore, this will go away. Right? The first term here, should this be given, is to say if we plug these things in here, is 0. Right? So that, I say, so that the first term of 3 vanishes, is gone, is 0. We don't have to worry about it anymore. What about this second one? So this is 0 now, and we are left with minus something here. Therefore, like if that is gone, therefore we can look at the Fourier transform of the derivative of f of x and find that it was minus 1 over 2 pi times the integral minus infinity to infinity, and then there was this factor of minus I omega in there. Right? So we had minus something minus. The minus goes away, we have I omega over the square root of 2 pi times the integral from minus infinity to infinity f of x e to the minus I omega x dx. But what is this? This is, does anybody see it? Yeah, exactly. This is exactly I omega times the Fourier transform of f of x. Or written like this, I omega times f of omega. But what has happened? We have reduced differentiation to multiplication. Let me draw you the corresponding diagram. So we just established what I will summarize in form of a diagram. is to say it as the Fourier transform reduces differentiation to multiplication, and we have that if we're given a function f of x and we want to compute its derivative to obtain f prime of x, we can do this directly, or we may compute the Fourier transform of this function, and we would obtain capital F of omega, which we may multiply by a factor of I omega to obtain I omega times F of omega, and if we back transform that, we get the derivative of f of x. And it is this property why humankind has developed this idea of Fourier transform. It goes back to a guy called Jean-Baptiste Fourier. He was studying problems that have to do with the dissipation of heat in sheets of metal, and came across certain differential equations, if that is being modeled mathematically, and turns out that these differential equations can be easier treated this way than this way. Even though these detours, right, involve fairly complex things, once you accept that these things can be done, then something that may be very difficult in its original form can be done in terms of something that is more easier. Okay, so we have now met our new friend, the Fourier transform, and the usual way it is introduced in most of the textbooks on image processing, at least that I'm aware of. They say the Fourier transform is defined like colon, and then there is this expression we just met, and then they expect you to accept it, and they take it from there. That's not how I roll. That is not acceptable. In order for you to really benefit from the experience of attending university, you have to understand where it comes from. Because if you understand where it comes from, you can easier work with it. All right? So what we are going to do, we are going to begin right now and continue throughout the next couple of lectures, is to understand where this thing comes from. And similar to what we just did, our direction of attack is the historical development. That is, we will try to retrace how mankind, humankind, came across these things. And once we have worked our way through that, I will reconnect it to everything else we have been doing so far. It is better that way. If I would reconnect it right away to the idea of vector spaces and so on, it might be a bit too abstract. So therefore, let us get familiar with what we just saw. Our goal now and for a couple of lectures is we want to understand the Fourier transform of a function say function of one argument defined over the reals, producing reals. This is how we begin. We'll later on extend that to functions from R square, like to sort of images, whatever. For the time being, we will focus on this simple case here. And our approach is as follows. So for you to have the bigger picture already, we shall study in order to develop an understanding of that, study first a finite series of periodic functions, and this is what Fourier himself did. We will then extend this to infinite series, and we will then later on extend that to continuous integrals. That is, the integrals we just considered will come back later. Right now we again forget about them. Now I said we are beginning to study this by means of considering finite series of periodic functions. Here is the next definition we need for today. What is a periodic function? So, I guess that is the last one we need right now. Definition, a function, and let's again focus on functions from the reals to the reals, is periodic with period p, so periodic, with period p if f evaluated at some x plus p gives the same as f evaluated at x. Who can name a function that has this property? Yeah? Sine and cosine, exactly. Right. So here is the canonical example, and I am really glad that you could tell me, because it is this one that we will study right now. Sine plus 2 pi is exactly the same as sine. The sine of x plus 2 pi is the same as sine of x. So this is an example of a periodic function. And I need to mention one more thing, and then we are good to go. The period of sine is apparently 2 pi. And so every 2 pi, the function sine repeats itself. We can force every periodic function to be a periodic function of period 1. So I'll just note that any periodic function of period p, in this example p is 2 pi, can be turned into a function, let's call it function f of lambda x. This is another Greek letter. I don't know if we have seen it before. It's lowercase lambda. Lambda x with period 1. Here is an example. We could consider the function sine of 2 pi x. This one is now of period 1, right? Because let's plug in 0 here, then this is the same as sine of 0. If we plug in 1, we get sine of 2 pi, which is the period of the original sine function, and then it repeats itself. Right? So sine of 2 pi is a function of period 1, and this factor lambda here in our case is 2 pi. Okay, now, and I just said this because from now on we can therefore focus. This is all very abstract study here, but we can make it even more abstract by focusing on functions, periodic functions of period 1.
Professor?
Yeah.
Maybe I'm wrong, but in the definition of the periodic function,
Yeah.
shouldn't we say that p is the minimal non-negative one?
Oh, well.
In this case,
Yeah. Okay. All right. You weren't there when I said it. I had this disclaimer at the very beginning of today's lecture that in all of what we are doing here, I will gloss over mathematical rigor because it would really take us way too far afield. So this is not a math class, and therefore I am just trying to provide you with an intuition of what all of this is. Of course, you are right. If it's of period p, then it's also of sort of period 2p, whatever, right? It's too many details, and I will gloss over them because we are not mathematicians. Right? I in a sense, I would have to be very precise here. But if I was as precise as required by mathematics, this would be way beyond what we should do here.
just,
Yeah.
in the example 2πx,
Yeah.
it's not very clear why the period is 1 and not 2, for example.
Yeah, but I just had this example that if you plug in 1, then you are sort of at where you would be with 2 pi. And of course, instead of 1, you could say this is a function of period 2 or 14 or whatever, because every 14 it repeats itself. I'm sorry about that. Probably should be so precise, but again, like if I was, then there were too many things we would really have to look into at a level of detail that is beyond what we should do here. So, without loss of generality, we thus study periodic functions of insert the f of x here once again. Periodic functions f of x of period 1, that is functions that repeat themselves every 1. And here is something more. I said, for the time being, let us consider problems that have to do with periodic functions. I will now specify the kind of periodic functions we are interested in. We also assume, and this is all just for the time being, but this is basically what Fourier did, that this function f of x can be expressed as a linear combination. Look at this. Linear combination, a concept we met earlier, over elementary building blocks. And by that I mean that we will now study properties of functions we can write as f of x can be expressed as a sum where the index of summation k ranges from 1 up to some n we don't specify it. And we have a coefficient alpha k, Greek letter alpha, times sine of 2 pi k x plus phi k. Here's another Greek letter, phi. And this is called equation 4. And the ingredients of this particular linear combination, we have a sum over something that depends on the index of summation, right? The k appears in the argument of the sign. And these sine functions here are each scaled by a coefficient alpha k, which also depends on this index of summation. And you may have heard it before, I'm just stating it for the sake of completeness. These numbers, alpha k, are called amplitude. Amplitude. And these numbers, phi k, are called phase. And then we have this 2pk times x. And instead of 2 pi k, we may also say nu k. This is 2 pi k. This is called the frequency. So there's lots of Greek stuff here. Here is yet another one. This is the lowercase letter nu. Latin equivalent would be n. In Greek it's nu. This is phi, something like f. This is alpha. This is pi. So why am I using those? Because everybody does. So this is just... Now, I am ever so rapidly just writing this down because, for the sake of time. On the website, you may have seen it already, I have a couple of lecture notes, not just slides, but longer, I mean they are shorter, but longer, shorter texts, say, where you can find all of this. Right? And actually there are lots of pictures there as well. In particular pictures that show the effect of choosing different amplitudes, different phases, different frequencies. So if you are not familiar with these ideas, then have a look at the lecture notes I provide on the website. Now, let's continue our study. Already early on throughout this lecture series, we met one of these addition theorems of sine and cosine. Back then it was about cosine. Now we recall that there is something like this, that we can, I don't know, if we're dealing of a function sine of some beta plus minus gamma, even more Greek letters, beta and gamma, then this is the same as, I hope, sine of beta times cosine of gamma plus minus cosine of beta times sine of gamma. And if I got it wrong again, you won't worry about the details. There is something like this. I hope this is right. It should be. We use that to write this equation 4 as, so instead of a linear combination over functions sine with argument something plus something, we do this now. Okay? And we would write 4 as, well, just put it on top of this here. F of x is given as the sum where k ranges from 1 up to n, and then we have some ak times cosine 2 pi kx plus some bk sine 2 pi kx. And I want you to verify this at home. So verify at home. Right? Convince yourself that we can write this like so. Probably try to figure out like how the AK look like if we turn this into this, and how the BK look like if we turn this is algebra. But do it at home. Verify at home. I'll use that a couple of more times today. Is this the best we can do in terms of studying periodic functions, or is there something else? So far, how would, here's an example of how something like that could look like. We have a 1 here. So say the normal sine, I guess, looks like this, right? But we can have, we have these different phases, we have these different amplitudes, we have whatever. Like basically, if we combine lots of sine waves like this with different phases, different amplitudes, we might actually get something like that looks like so, whatever. Very general, but it's periodic. Once we are here, it repeats itself. Right? Can look arbitrarily strange. Seriously, look at the examples in the lecture notes. But so far, all of this will basically at zero start at zero. There's no offset yet. Like, to be more general, we could require that we want these kind of periodic functions also to be located somewhere higher up or lower down with respect to the x-axis. And we will therefore generalize the thing we are talking about a bit more. So, to further generalize, we add a constant. And that is to say that from now on we will be interested in functions. F of x, that can be written as sum a naught over 2 plus the sum where k ranges from 1 up to n ak cosine 2 pi kx plus bk sine 2 pi x kx. Kx. This thing is called equation 5. And now we are there. This is the object of study. To briefly repeat, our interest right now is in periodic functions. To be fairly general, we are considering periodic functions that can be considered as linear combinations over elementary periodic functions. And depending on how we choose this alpha k, ak and bk, they can look fairly wild. And to make it even more general, we also allow for an offset term. And for reasons that will become clear later, I'll define it as a naught over 2. Right? And now we have fairly wiggly periodic functions that may, be somewhere high above the x-axis, somewhere way below the x-axis. This is how periodic functions should look like in general. Okay, good. And now things will become wild. This is a function defined over the real numbers, and it produces another real number. And all the ingredients are real numbers and real valued functions. But let us recall next, that e to the, be careful now, yeah, plus minus I 2 pi kx is the same as cosine 2 pi kx plus minus I sine 2 pi kx. Right? Why would I remind ourselves of this? Because if we look at this, look here, then we have some cosine plus something sine, which is very reminiscent of this complex valued function e raised to the I something. In particular, note that this are two equations which I squeezed into one, because there is a plus minus here and there's a plus minus there. So basically we have one equation with a plus and then the same equation with a minus. And if we look at this and consider the fact that these are two equations, we find so that because of this, we have that cosine 2 pi kx can be written as 1 over 2 times e to the I 2 pi kx plus e to the minus I 2 pi kx, and sine of 2 pi kx can be written as 1 over 2I times e to the I 2 pi kx minus e to the minus I 2 pi kx. And this is another of these instances you might want to verify at home. This is indeed extremely straightforward. Convince yourself that that is true. Now, then, if we would plug in our newfound knowledge as to how we can express the cosine and the sine of something into the two places where the cosine and the sine appear in equation 5, we get something like the following. Because of this, I can say, and we may write that this function f of x we are interested in can be expressed as, brace yourself, a sum where k ranges from minus n to n over a set of coefficients ck times e to the I 2 pi kx. This is equation 6, and I want you to verify this at home. Right? Check that this is indeed the case. Plug in our newfound knowledge as to cosine and sine into equation 5. See how you can simplify it, maybe how you can turn it into this form, and then in particular verify like what you would have to write for CK. So verify this at home. All of this indeed is true. Note the following, and I have to stress this. Note that in equation 6, summation ranges from minus n to n. This is a consequence of this insertion we just did. Right? If you really verify this, you will find that you can express the result in terms of this summation. This appears freakish because the K basically defines the frequency of these elementary building blocks, which we now write in terms of complex exponentials. And since it ranges from something negative to something positive, it appears that we include negative frequencies. This is strange, at least to me it was when I first saw it for the first time. And this is violating our everyday experience. Like, what should that be, a negative frequency? But mathematics doesn't care. Like, in terms of algebraic concepts, this is perfectly acceptable. But this is a difference to what we had so far. Back then it started at 1, and now it starts at minus n. And also note that this offset term, a naught over 2, is now somehow magically absorbed into one of these CKs here. Maybe say C naught. Right? If you verify this at home, you will find where the offset term has gone into. And also note that in equation 6, and this is another thing you will realize if you verify that at home, the coefficients CK are complex numbers. And this is another crucial difference to the form of the function we considered up until there. Up until there in 4, 5, this was all expressed in terms of real valued numbers, and now all of a sudden complex valued expressions appear. I encourage you to verify that at home. Okay, this is the situation we have arrived at by means of generalizing our idea of studying periodic functions as far as possible, and then we said, well, let's now that we had reached equation 5, let's now have some fun and express it in a form that that requires less writing, because this is considerably shorter than equation 5, but it is more abstract. Right? But it can be done, and for the last time, convince yourself that it can be done. We should then ask if there is any significance in what we just established. So our question at this point is there any significance, how do I write it, to these coefficients CK in equation 6? is there something, like, do they represent something we can make sense of? Is this something that can be traced back to a mathematical concept, maybe even to a physical concept? Okay. Now, what would you do in order to try to figure out if you can say something about these coefficients? The first thing that comes to mind is to use algebra and to rearrange this expression in order to isolate these coefficients on one side of the equation sign. And that is immediately and very straightforward. We have, so looking at this, this is a sum over lots of things. We can, instead of using this summation, really write C minus n e blah 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 plus and so on and so forth. If we do that, then we would move this term onto the right hand side, and one of these terms involving the ck on the left hand side apparently would then have to divide by e to the I2 pi, whatever k is. So we have, long story short, Cm can be written as e to the minus I 2 pi mx times f of x minus the sum where k ranges over all the indices not m, ck e to the I 2 pi kx. Do you believe that? Can you see that? Right? Apparently, yeah? No? Question? So what I've done here is I have subtracted all terms in this summation that do not involve m. I have isolated one index m. I have subtracted all the terms on the right hand side. So we have f minus the corresponding sum, right? And then on the right hand side in our minds we find Cm times e to the I 2 pi mx, and we have to divide by this number. But dividing by e to the I blah is to multiply with e to the minus I. Okay? So you see that. We can do that. This is in the true, and I'll just factor it out. So we get e to the minus I 2 pi mx times f of x minus, how do I write it here? Oh yeah. Sum where k is not equal to m, ck times e to the I 2 pi, and now k minus mx. I just multiplied this factor into this difference here, and then we have an exponential here, an exponential here. I can, write them together like that. This shall be called 7. Now, have we learned something? We have now isolated one of these coefficients, and it doesn't help us any further. And the reason is because in order to isolate this coefficient, we end up with an expression that involves all the other coefficients. And this is to say that, what can we say about Cm if that requires us to know the Ck? Not much. Right. And that is to say, let me write it down. We observe that Cm depends on the other Ck. Okay, this is sad, which is to say, like, so mathematicians again, time for your heart pills. In a sense, this is to say that, I'll quote it, mere algebra does not help on like that. Like just from rearranging the terms in these equations, we do not obtain deeper insights, and that is to say we have to or must resort to a bigger hammer. If this nail won't go in just using the hammer of algebra, we have to resort to a more powerful tool in our mathematical toolbox. And this is a very common trick in mathematics, and this is something which is basically impossible to teach, but this is something that comes with experience, and once it is there, it is totally intuitive to do so. What we will do now is we will integrate this equation and see what happens. Right. Hopefully after integration something disappears, and if that should be the case, we might have learned something. So yeah, why do we do this? I don't know. At some point in the history of humankind, mathematicians said, well, let's see what happens if we integrate. Oh, something vanishes. And once you found it at one place, you try it again and again and again, and it always works. Works quite frequently. So let's do that. And now is the first time that it pays off that we focus our discussion on periodic functions. Because integrating periodic functions, it is somewhat sufficient to focus on one period. So that is what we're going to do now is we integrate equation 7 over one period. And find for the left-hand side of 7, if we integrate that over one period, which is to say we consider the integral ranging from 0 to 1. We, after some discussion, agreed that we can focus on periodic functions of period 1. The only term on the left-hand side is this Cm, and now we integrate with respect to x, which is, of course, just Cm. A very trivial integral. It's already indicating that it's a good idea to integrate this equation because nothing happens on the left-hand side, which is nice because the left-hand side stays the way it was, which is basically what we want to consider. How does one of these coefficients look like? How does coefficient Cm look like? Okay, this is the left-hand side. Then what about the right-hand side? It's of course slightly more involved because the right-hand side now will be the integral from 0 to 1 e to the minus I 2 pi mx f of x dx. This is the first term on the right hand side. Now we integrate over it, minus the sum where k ranges over all indices not m, ck times the integral from 0 to 1 e to the I 2 pi k minus m x dx. Note that I have pulled the integral into the summation, but I can do that. Right? The integral over a sum of things is the sum over lots of integrals. No problem there. And I have also pulled out these coefficients ck, but I can do that. Because the integral over a constant times something is a constant times the integral over something. All right, let us call this thing here star and study it in depth. So this is what we will be looking at right now. I will clear the whiteboard once more. Star. Why focus on star? It looks as if it has a simple integral. Because let's say for the integrals in star we have, right, it was a sum over integrals, but let's just consider one of them. It's the integral from 0 to 1 e raised to the I 2 pi k minus m dx. This is a really trivial integral. Wait a minute, I'm missing an x here. Was that x missing on the previous whiteboard? No. Okay, so here it is. I don't know. I found it myself. Lucky me. So this is a somewhat simple integral, because this is just 1 over I 2 pi k minus m times I raised to the I e raised to the I 2 pi k minus m x, and we have to evaluate that from 0 to 1. This is just an integral over an exponential, very simple thing, luckily. Now, let's plug in 0 for x and 1 for x, and therefore we get, this is the same as 1 over I 2 pi k minus m times, first with 1, e to the I 2 pi k minus m times 1. And then we have to subtract all of this where x is 0, so it's basically e to the 0. Because if we multiply all of this with 0, it's just 0. And now, I claim, and there is another thing for you to verify at home, that this is the same as 1 over I 2 pi k minus n times 1 minus 1. And I want you to verify this at home, that this will always be 1. This here. Easy to be done. Check it out. But 1 minus 1 is 0. So all of this is 0. And that is to say that the second term on the right hand side of the equation we were studying disappears after integration. And we are left with the following. Therefore, and then we are done for today. Therefore, this coefficient Cm becomes, nothing changed on the left-hand side, can be expressed as the integral from 0 to 1 f of x e to the minus I 2 pi mx dx. Have we seen something like this before? We did not see this exactly, but I want you to compare this to equation 1. Compare this to 1. There, we had an integral that was ranging from -infinity to infinity, and then a function f of x times a complex exponential. There was, not really an m there, but something else. And there was also 1 over 2 pi in front of it, but it's not there yet. But basically, this is eerily reminiscent of what I told you is the Fourier transform of a function. We are not quite there yet, but we are getting there. Right? What we have done to reach this point is that we have said, well, let us, for the sake of the argument, consider periodic functions, and let's consider fairly general periodic functions. Periodic functions that can be written as linear combinations over very elementary periodic functions. With this offset term and so on and so forth. Then we applied certain things we know about sine and cosine to write our model in terms of complex exponentials. And in this rewritten form, there were these coefficients ck, and we have now singled out one of them and found that, we can use any of the indices for m here. So what we have found is that these coefficients that appeared in this algebraically, it was just algebraic manipulations of our equation for f of x. After some algebra, we obtained an expression in terms of complex exponentials and coefficients. And for these coefficients, we have now found that they can be written like this. And this is something we have, not quite, but very similar, seen earlier. And to wrap our discussion up for today, we note that the coefficients Cm are transformations of the function f of x we have been studying. This f of x appears within this integral. And another way of writing this is, instead of calling this Cm, quite frequently you may also find something like this, say f hat of m. Right? Because if you look at this is a function that depends on m. For different m's we get different values here, or different expressions. And here's the final definition for today. Definition: given a periodic function f of x of period 1, this function f hat of m is called the nth Fourier coefficient. So just once more, we are interested in understanding where this Fourier transform comes from, which we ever so briefly met as a way of simplifying certain differential equations. And we will use it in a different application context later. But today we saw the definition of the Fourier transform of a real valued function of one variable. And we are currently studying where this strange expression comes from. And to begin that study, we said, let us focus on a very special type of function, namely periodic functions. But they may be arbitrarily complex. That just depends on how many building blocks we add together and how we, I don't know, choose amplitude, phase, and so on and so forth. Studying that function, that class of functions, we found that we can express it in terms of series, finite series, where the index of summation ranges from -n to some n, and n is the number of building blocks, and then this finite series involve complex coefficients and complex exponentials. We asked, can we make sense of the complex coefficients, and this is what we found. We found that these complex coefficients again involve these functions f of x we're actually talking about. And this appears to be a special form of this general definition of the Fourier transform. So we are not quite there yet, but we're getting there, right? At least with respect to periodic functions, we have somehow developed an intuition for where this might come from. And the obvious question now is, of course, what if the function f of x is not periodic? Right? And this is what we're going to study next time, because this is all for today. Are there any questions? I have already uploaded slides for today's lecture. And on these slides, I have not traced out each of these steps we did here, but basically the major ones. So those you can find on the slides. All the details as to what we have been doing today is available in the lecture notes on the website. But I'm mentioning the slides because somewhere on the later slides, slide set 7, there are some tips, very rough tips for how to deal with these projects on the first assignment there. Right. So if you have not yet started working on the projects, then you should. And if you have started working on the project and you run into problems, then have a look at the tips I provide there. Okay. Well, if there are no further questions, then we see each other again on Monday.